So welcome everybody to this presentation in which I will introduce you to the Coriolis design flow, which is a free and open source flow to generate ASICs. Sorry. Oops. So here is the plan. First, I will make an introduction about why we need a free and open source design flow and all the reasons behind it. Then I will make a basic introduction about how to make an ASICs and the steps required. Next, I will present the design flow as it is implemented in Coriolis with all the various parts. And finally, I will make a little demo illustrating the rest of the talk. So what's an ASIC? Here is a picture of an ASIC, a very small one, so we can see what it is about. Basically, making an ASIC is making a big drawing. It's just a picture that you send to the foundry, which is a factory. So it boils down to a drawing, which we call a layout, and a specific drawing, which has to respect lots of drawing rules, calling design rule. So the fabricated object will work. So as I said, it's basically to make this drawing. So how do we get there? For I made this small flow chart to compare the design flow for FPGA on the left side and the design flow for the ASICs on the right side. So on the left side, you see the classical logical synthesis with free tool like Yosys. Then you can place and route with also a free tool like NextPNR. And all that tool, the end products of those tools is a bit stream, which just that you send, that you upload into a FPGA and that realize your design. And note that an FPGA is a kind of ASIC. It's a specific kind of ASICs, but one that you don't have to fabricate because it's prefabricated with some inbuilt capabilities. On the other hand, on the right side, you see the ASIC design flow, which I like is like the FPGA design flow, but more complex. I didn't put every steps in the right side, but still. So first, we have the logical synthesis, which works on a different basis than the FPGA, because in the FPGA, it's the resource built in the FPGA, like the LUTs and the soft blocks that is provided by the FPGA. Here, it's called a standard cell library. We will get to that a little bit later. Starting with the logical synthesis, we get a netlist, which is an electrical netlist, which is either written in VHDL or Verilog, the most common format for that. Following that step, we have the physical synthesis. That is, we put together all the bits to fabricate the so-called layout, which can be of two kinds, either symbolic or real in GDS. I will introduce the concept of symbolic layout also a little bit earlier. And the next step is to send your design, your layout to the foundry. The foundry is the factory which is tasked to transform your layout into a physical object that is a silicon chip. And then you get back your silicon chip. So this is the two design flow. Now, let's have a look at the size of the various parts of that stack, of that design stack, the ASIC design stack. And it is not exactly a stack, it is an inverted pyramid with a very pointed end, which is at the bottom. So at the bottom, we have foundries, which are held by maybe less than 10 companies, and maybe more plants, but still a very few number of companies. On top of that, we got the EDA tools that supply layouts to those foundry, and here again, there is a very little companies doing that. I think there is only 4 of them, 4 majors. People we are in the business will know them. It's very easy. Then on top of the EDA tools, you got the ASIC designer, which is currently, due to the limitation of this business, very few people considering the software designers. This pyramid, this figure is not up to scale. That is, it's order of magnitude bigger. You have order of magnitude more software designer than ASIC designer, for a lot of reasons that we will see just now. So it's dangerous, because if something collapses at the bottom, at the point of the pyramid, everything that's built upon it just crumble. We can also tell that making secure software doesn't make sense if the bottom of the stack is not secure. That is, running secure software on insecure hardware is inherently flawed. You cannot get something secure. So this is another incentive. Now, what are the roadblocks? Why are we in this situation? So I get back to my figure of my schematic of the design flow. So there are mainly 2 roadblocks. The first one is the cost of EDA tools here. As I said, the market of EDA tools is trusted by 4 big companies, and the price, the fees of the license of their tools are literally astronomical. I have heard, it's for sure, that to get the license for the full design flow of one company, it's about more than $10 million. If you want to have the full price, sorry, if you want to have all the tools, it's up to $10 million. So that makes sense if the cost of fabricating your design are high, but if they drop, it is not. The second point is secrecy. Secrecy that is kept by the foundry. The foundry, the layout that you send to a foundry have to respect strict rules, as I said, and those rules, if you look at the layout sent into a foundry, does give a lot of information about the physical process used to make the ASICs. And so it's a secret trade, and a well-kept secret trade, especially in the latest node. But here again, that makes sense for the latest node, below 22 nanometers, but for very old nodes or mature nodes, like 350 nanometer, 180, I would say that everybody has it. So there is no reason to keep that secret. Nobody has interest in copying you because they already have it. So those are the 2 main roadblocks that prevents the emergence of free tools. So I will come to the goals. Now that I presented the situation, I will come to the goals of Coriolis that we hope to achieve with Coriolis. First, we want to provide a platform for academics to allow them algorithmic exploration and experiment. For example, I have seen academics basing their experiments or their algorithmic exploration upon commercial software. And they did have a lot of problems because they were subject to problem to publishing, because it was so closely related to the software that the company didn't want them to explain what they did and how they did it. Or even worse, they make a work and then the company make an upgrade and there is no backward compatibility and all their work is lost. So that's a big problem. With a free open source, you don't have that problem. The second is to give the ability to publish, share, and modify the hardware design down to the layout, of course. So the idea here, the idea behind the scene, is to create a community. One of the main problems of people doing layout, due to the NDA imposed by the foundries, they cannot even share their work. Even if you are on the same foundry, have signed the same NDA on the same technology, you cannot share between you directly your designs. So you constantly have to reinvent the wheel. So it's block progress and the building of a community. By opening up the tools and the layout, we hope to build a community. Third, as I said, now you have technological node, mature node, like the older one, which are not so expensive. For example, you can have a run or you can have design made for 50,000 euros, which is quite reasonable. But if your design tool costs $1 million for a license, that's not possible. That's just out of reach. So we hope to help small businesses to enter this market. Of course, by opening up, like in software, like in Linux and everywhere, having something which is completely open and auditable allows a better security. So you can understand, you can check that the design is exactly what you send to the foundry. For example, if you can compare the layout you have with the layout of the design that was fabricated, then you can check if it's identical. And if not, you can guess that the foundry did something, like a material Trojan. And finally, we have another issue. For example, you have some project which requires a very long lifetime for their hardware. Think of, for example, nuclear power plant. They are designed to operate on a life cycle of maybe 50, even 60 years. And they are qualified with, at the start, with a certain kind of hardware, of processor, for example. So imagine that you need the same processor for a lifespan of 60 years or 50 years. That's, I don't know any kind of processor that can do that today. With free open source, you can do that. You can recreate, refabricate your hardware as needed and get exactly the same. So we do not do that alone. We are too small for that. So our first objective is to run on mature node. That is, nodes that are above 180 nanometers, because the tools are less complex that way. We will go down later, but for now, we want to achieve something that works on that kind of technology. So the target technology, the technology that we target today are the AMS 350 nanometer, the TSMC 180, and most recently the Skywater 130. In that idea, we just tape out in last July the TSMC, the LibreSOC free processor on the 180 TSMC technology, and we are currently awaiting the return from forum packaging. So we hope to have it in the next months and start to test if it works or not, or if it partially works. So we also have collaboration with Professor Naoshiko Shimizu from Tokai University, which is already a user of Coriolis and has made design with a wide range of Japanese technology. Fenitech, ROM, and Hibikino are Japanese technology, but they can work with our tool. He configured our tool to use them, and he makes design that works. Small one, yes, but still it maintains the competence. We also collaborate with Staff Verhagen from Chips4Makers, which supplies us with optimized library, standard cell library on macro blocks. We will see that in a few moments. What is it which is providing us? So, okay, now let's have a look at the difference between symbolic and real technology. So on the left side, you see the symbolic technology, which was created in the 80s by two American professors, Mead and Conway. They are famous in our field. So it was based on a simple observation, which was that if you change technology on the same node, for example, you take the 180 technology from TSMC and compare it to the 180 from Intel or from Global Foundries, you will see that, in fact, the layouts are quite the same. Not exactly the same, but very similar. So they said, we will make a blank unit called the lambda, which is just an anonymous unit. We will draw all our cells and design using that unit. And when we have to get to the layout, to the foundry, we just perform a scaling by telling, for example, that 1 lambda is equal to 1.5 micron. And just by that, we generate a valid layout for one foundry. It had many advantages at the time, which was to be able to target multiple foundries with the same design without redesigning each time the standard cell library and remaking the place and route. And it was also able to cross between nodes. I mean by that if you design something from 350 nanometers, it can be easily ported to 180 nanometers. On the left side, I represented the way Alliance do that because we made a little improvement over the raw scaling. Mead and Conway just made a direct scaling. What we do is add some flexibility by adding a delta W for the width of the segment and the delta extension, a delta E, so that we can more finely tune the mapping toward the target technology. Of course, it has a cost. The cost is that your design will be slightly bigger. It will use a greater area than if you use the real technology directly. Depending on the technology, it may be between 5 to 10%. So it's up to you. But the advantage is that the symbolic is publishable. You can publish a symbolic layout. There is no NDA, no string attached. So it is something that was not foreseen at the time. Symbolic layout abstracts you from NDA. So it's still an interesting approach, even when the design kits are starting to open up. So for our latest realization, we did use an hybrid approach with FlexLib. This approach was designed by Staff Verhagen from Chips4Makers, and the idea was that to keep, for example, the NSX-lib block diagram, the standard cell library block diagrams, and to map them precisely to the technology. this way, we can design the technology once, the library once, and then directly map it to the technology. The idea here is not to have to redesign the standard cell library each time you change of technology. You design the library once, like a stick diagram, and then you just map it to the technology you want. So you save a tremendous amount of manpower. So this is the third approach. And unfortunately, the result of FlexLib is still under NDA. So now I will make a little bit of history about our work, especially Alliance first, which explain some kind of clunkiness in our tools. We have different tools coming from different sources. So this explains why this is so. So first, Alliance, which was fully open source design flow in the 90s, and which was symbolic. It was purely digital and fully symbolic, but it was a complete toolchain. It includes the logical synthesis, the physical synthesis, and all the checking steps. Then, starting from the 2000 years, we redeveloped Coriolis, which support both symbolic and real layout, but it's only the place and route part which was re-implemented. It is not the logical one. You cannot synthesize something with layout, with Coriolis. In the end, we build our toolchain like that. So we use the Alliance tool for the symbolic layout, for some part of the symbolic layout, and mainly for checking, for verification. We use Coriolis to make the place and route, and we use Yosys for the logical synthesis step. And binding that together, we provide also the Alliance check toolkit, which provide a set of examples and tutorials to use the toolchain and provide an some level of automation through a makefile. So a little bit detail about the design flow assembly that was used especially for the LibreSOC design. It was done with NMiGen for the HDL part, the hardware description language. GHDL was not exactly used in this context, but still we use it for VHDL simulation. Of course, the ubiquitous Yosys for logical synthesis, the FlexLib library from staff Veragen, and Alliance and Coriolis for the place and route and some checking. We also use from time to time K-layout to check the GDSII. And finally, LibreSOC did put that together and did use all the tools to make their chip. So now I will go to the part of, I will go into detail, how do we make an ASIC? What are the steps and what are the challenges that we are facing when making an ASIC? To have a good understanding of what we do when we make an ASIC, we must understand the basic of the flow. The first part is to start from the RTL description of your design, which is a set of Boolean equation and registers, register, transfer, level, which is in Verilog or VHDL, whatever. Then you run Yosys, which will use the standard cell library to create a netlist. The netlist, the standard cell library is the blue part at the bottom. So Yosys use that to create a netlist which is built upon only those standard cells. And those standard cells have the main characteristic, the main property, to be exchangeable with layout. They have a layout counterpart. That is, you can translate a logical function, here an AND, into its small layout. Then, the physical synthesis reassemble all those little bits to form a complete design. it draw the wire, it perform the placement, it place them on a plane, and then draw the wire. And in the end, it gives back the layout, which is the equivalent of the RTL, but that can be sent to the foundry, which is a physical object to be done. So you see, this is a V-cycle. You disassemble on the left side and you reassemble on the right side. So now we will see how to reassemble. First, a little detour by the standard cell library, which was made by Naoshiko Shimizu. It was by starting from Alliance template, which is called ASICs-lib. He built upon it an NSX-lib library, which is more flexible and portable. It contains 89 cells, which all the things that you can expect in that kind of library. Logic gates, I mean logic function, the flip-flops and multiplexers. The interest of that library is that it has been already used in some design, I should say many design, so we are confident that the transistors are correctly calibrated and designed. So it's a working library. And it was used by FlexLib as the base from his stick diagram library. That is, the general shapes were abstracted to be able to be redrawn in the target technology. But it's still the NSX-lib which serves as the base. So what is the placement? Here I represented a small netlist in its logical form on the left side. So you see logic gates like this is XOR, AND, OR. And what we do is replace those little bits which have their layout equivalent like that. And what we want to do is to place them in a square, usually square area of silicon, where we can implement that. They must be placed following two criteria, at least. There are others, but the main criteria are there should be no overlap between, of course, two layouts of the cell, no overlap between this one and this one, and the wires, the length, the total length of the wires connecting them must be minimized. The less you have wires, the more efficient your design becomes. It becomes faster and it uses less power. So this is the structure that was adopted a long time ago. The cells are put in rows. They are not put in arbitrary position, not fully arbitrary position. They are put in rows, and the rows share their power lines. For example, here at the bottom, it shares with nobody, it's the ground, VSS, and then the first VDD is shared with the one. So one row over two is flipped over, flipped vertically. This is the sense of the arrow. The arrows indicate the spin. So we have regular slice and regular rows. So this is the work of the placer. It's a complex task, but in the end, this is what you get. So now, before talking of the routing, global and detailed routing, let's have a look at how the metals are organized. In fact, they are, we call them layers, metal layers, because they are organized in planes that are put on top of each other. And in order to, they are connected through vias, it's also called cuts, for example. And you see here an example of the stack, of the metal stack. We have metal 1, metal 2, metal 3, metal 4. This is a mistake. This is metal 4 here. And in order to perform the routing, we have to assign them preferred direction. This is not required by the technology. This is required by the tools in order to work. Otherwise, the problem is almost unmanageable. So what we do is assign their direction. For example, the metal 1 is vertical, then the metal 2 will be horizontal, and then the metal 3 will be vertical, and so on. The metal 4 will be horizontal. This way, we create a Manhattan grid. We have a complete routing grid, which is done in Manhattan. there was trial of making X 45 degrees wire. It didn't succeed. So everybody got back to the simple Manhattan structure, which allows horizontal and vertical tracks. Now that we know how we make tracks and how we build the wires, this is what a router does. Over the area of the standard cell, what you can guess behind the cyan horizontal line and red vertical line is the layout of standard cells that have been placed. So we put over that the tracks, and vertical tracks and horizontal tracks. Here I only represented metal 2 and metal 3 to avoid completely overloading the drawing. So the problem for the routing is that this represents a tremendous amount of data. If we try to route directly on this representation, we cannot succeed. At least the memory of your computer will just explode. It cannot manage that, except for small design, of course, but it is not exactly what we are interested in. So we must abstract the concept. We must make a simplification to make the data manageable. What we do is a two-step approach. First, we transform a square area into a point, which is called a G cell. That is a 1 G cell. This area here is 1 G cell, and we abstract it into 1 point. 1 point in a complete grid, a graph, and then we route on the global graph. So this is the explanation between global routing and detailed routing. The global routing works on the global graph to find approximate paths for the wires, and then we finish it with a detailed routing. So this is the global routing here. So we have the node. Each node is an abstraction for the G cell, is a representation, a compact representation of the G cell, connected with its neighbor by edges. And you see here the capacity of the edges is the number of tracks that can go through this edge, the horizontal connecting edge. The same goes for this horizontal edge. So this is how we do the global routing. Now that I detailed the place and route steps, I will just introduce you to two electrical problems. Those problems are slightly are a different kind than the previous one. They just interfere with them. The first one is for the high-fan-out net synthesis. The synthetizer, for example, Yosys, do not care about the power of one gate. For example, here the driver, if it's an AND, will be connected to any number of gates, for example 8, without regards of its power. So maybe this power is not enough to drive adequately all those inverters. This is something which is determined by the library, but imagine that it is not enough. What we have to do is insert buffers, a stage of buffers between the primary gate and all its things. So now we have two buffers and we have one step of buffering. If you have more things, you may have multiple stages of buffering. This is managed by I think it's exponential. You have to have an exponential number of buffers for each stage. So this is the first problem that we can encounter. The second problem, I see maybe the time is a little bit short. So the second problem is that when you have not only a problem with the power, but also with the timing. That is, for example, for a clock. you want the clock signal to reach all the DFF at the same time. And that, if you let the router manage the wire as usual, it will get something very bad. Each DFF will get the clock signal at some time. So here is one of the first approach, the one we use in Coriolis, is making an H tree. That is, we are distributing evenly through buffers, but buffers organized in an H tree at strategic points. And here, at the end of, at the leaf of the tree, you have normal routing between the DFF. But this way, we can be sure that the difference of arrival time of the clock signal will be strictly limited. So this is the H tree. And it can also manage other signals like the reset, for example. In our design tool, we also impose a fixed hierarchy. That is, if you want to automate the place and route steps and the making of an ASIC, of a full ASIC, full chip, we impose that structure. That is, the design is the netlist supplied by the user, which is the core, and then we wrap it inside the Corona, which makes the interface between the Corona and the whole chip and its pad. Then you have the Corona, and you have the chip, which is the top level thing, which is containing only one Corona and all the I/O pads. The nomenclature is here. So this is to automate the design. Now we have a problem with our tools. This is explained here. The problem is that you cannot optimize one without optimizing the others. The problem is that if you tap on this one will go up. This is exactly the same problem that we have with our tools. You cannot optimize separately each stage. You must optimize all the stage at the same time. That is, the placement depends on the routing, which depends on synthesis. And you have to try to find a way to do that in parallel, which is the big problem of those tools, of the kind of tools. So it has a consequence for the software. Our software is based on a database which allows the tools to communicate between them. They live in memory at the same time, and they can exchange information, especially between the global and detailed router, and they can make requests between them. And we can have some kind of mixed optimization. Now, another point of Coriolis is that it's tightly integrated with Python. In fact, only the computational intensive part are written in C++ under the form of a Python module, and the whole glue which makes the software works is in Python. There is not even a real binary in Coriolis. It's only Python scripts. So if you are not satisfied with the way it's initialized or works, you can completely rewrite the initialization on everything that works around, as long as you get the initialization done correctly. So I will quickly pass here for the physical synthesis. This is the contents, just a brief description of the content of the design, which explains the fusing between C++ and Python. You see each part. This one is done in Python, building the floor plan. Then we perform the high-fan-out net synthesis in C++. We build the clock tree trunk. Then we place the standard cell, and after building the standard cell, that now we know where the DFF are, we can connect them to the leaf of the clock tree. So this is an example of interleaving the placement and the routing. Then we perform the global route. We can perform insertion before the detailed route, and then perform the detailed route. So it's all completely fused. I will go quickly on the flow itself to go to the demonstration. So what we have here is just the design flow in symbolic, and if you want to run it, just perform the rule, make layout. If you have a configured design like in Alliance Check Toolkit, you can just perform a make layout and it will do everything. all the flow. For the real design flow, it's almost similar, but you will not be able to distribute, of course, the GDS, and it's slightly shorter. So, and here you can do make GDS. Finally, the logical synthesis is done with make VST, and you see a lot of different programs, like NMIGen. We can generate RTL or VHDL. So you can attack the synthesis, the logical synthesis, either with VHDL or Verilog, or even an HDL language, which in turn provide Verilog or VHDL. So it's still a bit too complex. In the future, we hope to fuse the different tools so that it's there is less file exchanged and it's done all inside tools. So we can also, when we run in symbolic, we are able to perform some validation. We are able to perform a LVX, which means a layout, a netlist comparison. We compare the netlist, which is the original netlist, with the netlist extracted from the layout, to be sure that the router has done its job correctly. In the same way, we can check that the layout respects the symbolic rules. Here. So this is what we have done. The LibreSOC chip, which is 1.3 million transistors, of which 800,000 are in the SRAM, sorry. 500,000 are in the standard cell. The RAM is here. Now we have the area, 28 millimeter, and now we can proceed to the demo. Okay. Alors, I will use a demonstration which is already present in Alliance Check Toolkit, so CMOS 45, which is a symbolic technology. So the first step is to make the VST. As I said, you can just perform make VST, and everything is taken care of. You see the Yosys call, and finally the translation from the output format of Yosys, which is BLIF, into a VST format, which is a netlist. So now you can either process in a text way and run make layout and just get the layout, but for the purpose of this demonstration, I will use the graphical interface. So we just make CGT, and we get the graphical interface. Before running the script, the famous do design that I talked about earlier, we can have a look at it. It's a very simple script which contains the most verbose information is where to put the I/O pads. Here, you have two things. We can use it as a block or use it as a whole chip. So if you are using as a whole chip, you have to specify where the I/O pin goes. And if you use a block, you just tell where the pins are. Then you set up some specification about the size of the chip, the size of the core, and so on. And for also the purpose of the demonstration, I will put it in debug mode. I will activate the breakpoint so it will stop between steps. And I can run my example. I hope I will be able to grab the handle.
Background make CGT is stopped.
Ah, you're right. Yes, works better. Thank you. Ah, the handle is too. Ah, là. Okay, so now I will load the design. Just run the script, in fact. So here is the first step. The root of the clock tree has been done. More precisely, what you see is only the place where the tree will be put. The buffers of the tree will be put. So no placement has been performed yet because the standard cell will be put around them. So I will just make a little zoom so we see better the placement. So now the wire making the hatch tree has been done, not the end connection to the DFF, because the DFF are not placed yet, but the clock tree, the tree here is completely done. So now we see the placement. I did choose a very small example, so it doesn't take too long in graphical mode. So this is the simple algorithm, and you see the spreaded configuration. You have in a simple algorithm, you have two configurations. The one which is is guaranteed to respect the density, and the one which is compacted. So this one respects the density. And we stop when the differential between the compact and the spreaded one is less than 10%. So it will stop in a few seconds. And we'll perform the last step, which is legalization. Legalization is putting the cell exactly in rows, because the previous step didn't put them, as you have seen. So here we have the cells. The filler cell have not been added yet. So this is the next step. Okay, so now the filler cell have been added. You see also that the power line have been created, and the violet lines are the fly lines of the nets. If we look at them, for example, here, we can load the netlist and require the displaying of one of the fly line. So, but of course, it has to be visible. So here we are. That's the fly line of one net. So you can see you have some funny nets. So I will just select this one, and this is 8.2. No. Where is it? I want a nice one for the demonstration to be funny. It has to be a little bit bigger. 684. Okay, that one. So we are before the global routing, and here we just have the fly line, and now we can perform the global routing. Here the global routing has been done. So I think I did select a very small net, so it's less funny than others. But what you see is that the global router has made the wires just center to center here. And one interesting thing with Coriolis and for academic is that you can add layers. I mean, you can visualize what your algorithm is doing. For example, here, I will highlight the edges. I will highlight only the edges, so I undisplay everything and require only the edges. So what you see here is the density of the edges. I will unselect, so it's brighter. What you see is the utilization rate, the capacity utilization of each edge of the graph. So if we go closer, you can see that there are 4 edges used over 12. So you can debug easily your global router, for example. And each tool can add exactly what he wants. You want display whatever you want. Just it's written in Qt, so you can add whatever information you want in overlay of the design. For example, we also have the G cells. So here are the G cells. So now I will redisplay everything for the next step of the presentation. Alors, display everything and just hide the edges and the G cell. So it becomes clearer. What should I know? I know. It's the grid. Okay, it's the grid. Okay, it's just a small default at this level of zoom. It shouldn't show. So now the last step is to perform the global routing. The detailed routing, sorry. It's done here, and it has succeeded. So now we have our design. And it is finished now. So you can see we have also the I/O pads and the whole design. We can also perform here the checking of the netlist. See that the netlist is exactly what it should be. So for example, if you make LVX, I hope it won't work, it will work, sorry. So you see here that you got an extraction with the Cougar tool, which takes the layout and the symbolic layout and get a netlist back. And then LVX performed the comparison between the netlist and the reference netlist and the extracted one. And of course, hopefully, they are identical. Netlists are identical. So this is my small demonstration. We have also, so for this example, I support CMOS 45, a version for FreePDK 45, and lately Sky 130 is work in their progress. That is, it plays on route, but still there are design rule checking error because the cells are not quite finished. There are DRC error, but they are not in the router itself, they are in the cells. So I won't show you that example. So now I think I am way over the session, so I have finished my presentation.
I think we're not interrupting anybody else because the other room is on a separate Zoom.
Can I ask a question?
Of course.
So this final netlist, can you actually run it through SPICE with the full analog models? The entire chip? Would that just be too intensive?
It depends. If your chip is small, you can do that. For example, at our labs, one of our colleagues did use that structure, that netlist, that little chip, to perform a SPICE simulation. But if you are going too big, for example, even a medium-sized chip like the LibreSOC will not be able to run under SPICE. I can provide SPICE netlist. Everything is fine, but it's too computational intensive, unfortunately. What you can do is select some nets. You can extract part of the netlist and just run those nets. And even that could be a very interesting information. If you know what nets to pick up, what critical nets to pick up, you can simulate them.
Yeah, I think that's very, very exciting because having such capability is almost impossible at any small scale. Just like simulating how your chip performs with a particular net.
Yes. So it's one of them. It's not very complicated for me to do. Just as always, lack of time. But I know exactly how to do, and it's not very complicated with the data structure.
And I had one other question is, have you tried the reverse process of taking a netlist and turning it into a symbolic? So trying to deduce what the active device, what the your semiconductor is meant to be? What type of transistor or diode?
I not exactly understand what you want to do. We cannot reverse back a netlist. A netlist is just a netlist. It's not layout. So you cannot
say, for example, you had a cell.
Mm-hmm.
Would you be able to, does your tool have a capability of taking a cell and deducing from it where the PN junctions are and trying to figure out what the device is. I guess that's just too complicated.
Not exactly. In fact, this is exactly what Cougar can do it. The tool I just run here has two modes. One mode is in Netlist, in the gate level. That is, you stop your extraction at the gates to get back the netlist in terms of NAND, NOR, and so on. But you can also have an extraction in terms of transistor. And that way, you really know the transistor. You have the full SPICE netlist. And moreover, I didn't present it in this presentation, but you also have TAS and YAGL, which are tools that are made by our lab, which from the netlist of transistor, at transistor level, of SPICE netlist, can recreate the logical function made. For example, if you have a NAND, it's able to tell you that, okay, those transistors are making a NAND function, a NAND logical function. So yes, we can do it, but it's that needs a lot of polishing.
Yeah. Oh, and one more thing, these technology nodes you have, how do you include them without having an NDA? For example, the TSMC one.
The TSMC, I cannot, of course. What's in this directory, which is public, does not contain any information related to the technology. That is, you cannot run this example, for example. You cannot run this example. You need to have additional information that I do not distribute, of course. But for example, Sky 130, it's possible. And FreePDK45 is also possible because they are free technology. But of course, if the technology is under NDA, it's not possible.
So, Andre, what I did, Jean-Paul and I worked together side by side. So I did, because it is the same program, the same do design, mostly, I did things under the free PDK45 library, and then Jean-Paul was able to do the same thing under the TSMC one, the NDA'd one. So, and that saved us time. Now, once he'd done the layout, he couldn't tell me about it, but you know, or show me it. But at least I was able to help him to complete the do design .py code, and then he could actually check it under the 180 nanometer.
Sure.
Because the tool works exactly the same way. And we have especially configured the FreePDK45 like it was the TSMC one. That is a six layer of metals, and we changed slightly the pitch and so on.
I also had to create a couple of fake cells. One was for the PLL and one was for the SRAM, so that I could place those fake cells under the free PDK45 without having to know about the NDA cell or the sizes or any information about them at all, except for what the inputs and the outputs were to the block at the overall level.
Yeah, it's amazing. I don't know if it's if it's one of the most important CAD tools. There are so many of them, but these ones, like Yosys and this one.
It was difficult to make it. I mean, the placer was made by a very smart guy, which is use SimPL. The global router is quite ordinary. I mean, in terms of algorithmics, it's a standard algorithm, but the detailed router is quite advanced, in fact. It's a real research tool.
I wanted to ask you about that. Are you aware that the military way of doing coordinate system is based on a 1 to 9 grid?
On a what?
1 to 9 grid, so number like a number pad. So the number 5 is in the middle, like the you know, like latitude and
On your
longitude, but
phone.
they use the numbers 1 to 9, and you subdivide further and further down. Would that technique actually be useful, so that you did a massive grid? You divide the global routing is only 9 squares, and then do a subdivision of those 9 squares into 81 squares, and then divide into 200.
Like a fractal.
Yeah.
In fact, it was envisioned in an earlier version of the placer. It was not by 9, but it was by 4. You mean the classical quad tree with a progressive refinement. In fact, we didn't achieve it because the guys tasked with that did live in the middle.
Oh, bless.
So we weren't able to do that, and then we switched to SimPL. But it is an important feature. I think we will explore it again in some way. What you are defining is some kind of progressive refinement. That is, you don't place then global route, then detailed route, but you make roof placement, make estimation of the global routing, and then go on.
Oh, cool.
Do I make myself clear or not?
Yeah, no, it's fantastic.
It's clear in my mind, but
yeah.
So it's a very important feature.
Sorry to interrupt. Do you know if there's any effort to do something like RF, MMIC design? Or is that just an extra complexity level above?
Not yet. Another thing that I didn't show here is that I can seamlessly mix with analog design, not RF, but still analog design. There is already inside Coriolis a support for analog design. And the fun thing is that it's completely mixed. There is no concept of analog on top or digital on top. It's just an uniform way. It's completely uniform.
The only difference is you'd have to add some extra rules, wouldn't you, to make sure the analog is, for example, cleaner than digital in some areas.
Yes, of course. It's not routed like digital, of course, but it works. That is, it's the global routing structure can support analog design, and the detailed router can support analog parts with specific rule. For example, symmetry. You can add a symmetry constraint inside the router and tell them, okay, this wire on this one must be fully symmetric, and so on.
Very cool. Thank you.
Thank you. I don't know if there is any question. I think I will close the presentation.
No, thank you. That's fantastic.
So, okay, so thank you for listening to me, and I hope to see you in the flesh sometime.
Sure.
So bye-bye.
Thank you very much. Bye.
Thank you all.